certified professional agronomist, and I'd like to talk to you briefly today about an element that we use in large quantities in agriculture called phosphorus. Sadly, phosphorus and its chemistry are grossly misunderstood. And oftentimes, we're out here trying to really apply materials in high levels that we don't understand, thinking it's going to be more helpful for us. And when we do that, we don't understand what kind of things that we mess up. So, this is all about phosphorus's use, understanding its chemistry, its measurement, and how to make it more efficient. How is phosphorus even a part of our system? Well, we have to look at energy production. Number one thing that's involved with it is energy production. When we look at biology, whether it's soil biology, human biology, animal biology, plant biology, phosphorus means energy storage and production. Phosphorus is stored in this complex picture here. You see the little elements that are created with the little letter P involved. And where the letter P is involved, those are bonds of phosphorus to other things. And the piece on top is called ATP, adenosine triphosphate. That's where phosphorus is stored as energy. And then as it's needed down the right side there in energy transfer and certain reactions, we lose the phosphate energy and it falls down to adenosine diphosphate on the bottom and then is reactivated through energy cycles and turned back into ATP. So it's like a battery being discharged and recharged, discharged and recharged. And in this complex picture that we have here is the most important part about phosphorus. Now, it's also involved in protein metabolism, metabolism meaning build up, so making proteins. And it's also involved in sugar production, energy production as part of sugars in the plant. So it's a very important element tied almost completely to energy production. So now, if we think about what we've done in the past, we measure phosphorus. And when we get soil tests back, we don't realize that the phosphorus number we get is not what we have all in the soil. It's only the available portion, in some cases, of thousands of pounds of minerals. And so our testing for phosphorus total is incomplete. It's only the available piece. And so as a result, when we see that, we think, oh, if our level is low, we might be completely out of phosphorus. That's not the case. And so we add phosphorus to try to get our soil test levels up. And so its chemistry can become our friend or foe, because our idea is, since we don't understand it, let's just put a lot in there and let the plant figure it out. It sounds like a good idea. And especially when we're told if we put it into the bank and we don't use it, that maybe it'll get used later and stored. But that's not a very good idea, and here's why. If we look at phosphate chemistry, the fertilizer itself is made by reacting sulfuric acid with a mineral called apatite, calcium phosphate. This, see my teeth here, teeth and bones is apatite. That's where it comes from in South Florida. And so what they do is they pull that phosphate out, they treat it with sulfuric acid, it melts into a liquid material that basically is making phosphate fertilizer. They turn that then from a liquid material, in most cases, into a dry material. You buy it as 1846 or 1152 or 0460. You take it out, you spread it on the field, and then when that fertilizer melts with rainwater and starts to dissolve, it starts moving down into the soil. Well, ironically, because it's a very unstable compound, once it actually runs into a few other elements, if it's not picked up pretty quickly, it ties back up, in many cases, because calcium is so readily available in our soil, into the same calcium phosphate. Remember now, that's not soluble, that we had before. So it locks it up. Not only does it lock up calcium, but it locks up manganese and zinc and copper and iron, elements that are metals. And if we get lots and lots of extra phosphate, we end up tying up what little availability in many cases of our micronutrient metals are there too. So when we upset the apple cart with too much phosphate, we tie up elements that are extremely important in making us more efficient in our plant and soil system. So we have to oversupply those. So it just ends up being, when we apply too much, we don't realize when we're shooting for high yields, we have to apply more copper, zinc, manganese, iron. We have to plant all these other things, apply them, and it just drives our costs up. And we don't even know that it's going on. Okay. So if we also tie up that phosphate along with those other nutrients, it's not working in our plant either. So it's kind of sinister. So if we actually think about the phosphate itself and making it available, there are some things to be considering. And one of those is not all phosphate is the same. There are different forms of phosphate, and we can actually time when we want to use it to be more efficient. Within phosphate itself, phosphate fertilizer, if you buy 1034O, you're buying a product that has a little bit of orthophosphate, maybe a maximum of 30% of the orthophosphate form, which is the available form for the plant. The plant has 10 times more sites on its roots to absorb primary orthophosphate and a little bit of secondary orthophosphate, some more chemistry again that we don't understand, than any other element in the soil. That's how important it is. And a lot of those sites are on the little teeny tiny hair roots that are on there by the billions and billions, countless numbers on all those major roots that we look at. And we pull them out of the ground, we saw those little hair roots. That's where most of the orthophosphate is absorbed. The other portion of that phosphate is polyphosphate. Polyphosphate are chains locked together and are unavailable. Now, polyphosphate will be made available and turned into orthophosphate in time and can even be done during the season that we apply it. And so microbes, temperatures, heat as it comes into the soil and drives microbiology can help us change the poly over into ortho, but it takes in some cases a matter of weeks. So if we had some kind of combination of orthophosphate with poly, we'd have in some cases the best of both worlds, readily available stuff immediately and slow release stuff later. And so when we make up a product like 725-5, that's 80% ortho available phosphate and 20% poly of slowly available phosphate. So that makes it available throughout the season. The most important thing is if the orthophosphate is readily available and it comes around tiny hair roots and in the root zone, why in the world are we applying it all over the place? Because only where the roots grow and have a lot of these little hair roots is it typically being picked up. Now we got to think about these things because it does help us understand a little bit how we can be more efficient. If root mass requires huge amounts of phosphate to form, and when plants are growing, they take energy to grow. And then when they switch over to reproductive phases, it takes a huge amount of energy, thereby a lot of extra phosphate. So just throwing it all out in one great big flu at the beginning of the season and hoping it stays available, you begin to now see the efficiency of this thing is starting to come into question. So if that's the case, and we can understand that we have orthophosphate forms and we put them into, let's say, starter solutions, or in some cases foliars, which we'll talk about here in a few minutes, can we be more efficient? And the answer is yes. But one of the key things that we can do is to actually put additives into this material at the same time we're applying it in the early part of the season. And lo and behold, new magic can start to happen. We can take things like microbes and apply them with the fertilizers. And the microbes actually respond to signals from the plant saying, hey, I need some phosphorus here. And microbes are living organisms between a living plant and a, if you will, a dead soil mineral system. And they produce acids and enzymes that actually melt phosphorus out for the plant around those little tiny root hairs. And the plant will send out sugars, amino acids to keep growing those particular microbes that are releasing that phosphate for them. And so when we add in those microbes, they can do multiple jobs, including this one that's very important for phosphorus. And that's been going on since the beginning of microbes and plant interactions. So the other thing we can do is we can actually throw in that same sulfur that we talked about a while ago that melts the phosphorus, as you see in these pictures, because these are going to be tissue analysis that we're going to look at. We can throw in some ammonium sulfate or ammonium thiosulfate that will actually melt, in a sense, into a little bit of sulfuric acid and cause phosphorus that's been formed into that calcium phosphate. Remember, teeth and bones, it's insoluble. If we put sulfur in the system and it comes in contact with that calcium sulfate, it melts it. And if it melts it right there near the roots, lo and behold, phosphorus is released. It also at the same time releases zinc, manganese, copper, and iron, metals that when you pour acid on it, it melts. So uses of other fertilizers can make our phosphate more available. In this picture you see in front of you, these are two separate farms for separate locations on those two separate farms. And you see the measuring date for the tissue analysis underneath it. And the red and the blue lines are the industry standard, saying if you typically can kind of be in that vicinity above the red line and close to the blue line, you're going to be close to the industry standard for what we want for phosphorus in the tissue. Look at these two separate farms above and below. And this represents, in this case, 20% less total phosphorus applied to these fields than the local grower standard. And look where the tissue levels are. They are, in some cases, a third to twice as high as they would have been if we just used an industry standard. What's in this? Well, this is a situation where when we put product in the furrow, we had microbiology, the orthophosphate products, as you see, a product called Infuse, which you'll learn about later in another video, that has micronutrients, microbes, and food sources in it, as well as an added quart of fulvic acid, food, if you will, for both the microbes and the plants to grow them and sustain them. And then around it, it has sulfur with more humic acid, food sources for the microbes to allow this thing to be constantly releasing. And look at the phosphorus. The bottom line is in all of these tissue levels, they're all way above where they could be. And inside the plant, they represent the energy formation. So the energy levels are extremely high in these plants. And look, in some of them, they even begin to fall off toward the end of the season, which is what you would expect because the tubers are calling for the energy to begin to fill. So it's normal for those levels to begin to fall. But at that much higher a level, you barely even fall down to the industry standard. So this is the exciting thing. This is helping us understand how phosphorus is in the soil, how it's released from the soil, how it's released into the plant, and not sitting there saying, look, let's just build soil test levels of phosphorus however high we want. It doesn't make any difference. The plant will figure it out. You mess up the chemistry and the plant struggles through, it still is able to make yield, but it never optimizes yield. And that's what this discussion was hopefully all about for you. Learning that you may not need quite as much phosphorus to get as much or more than you've ever had. These folks were rewarded with a very, very nice yield improvement with a much lower cost of investment. That is efficiency and return on investment. If you have questions about how to make this program work for you, get with your representative to get those questions answered.